Okay, so having seen the basic things on addition of natural numbers, we are now going to see multiplication. Now this is a new section, section 2.3. So we straight away see the definition. Definition 231. Multiplication of natural numbers. Let M be a natural number. To multiply 0 to m, we define 0 times m is 0. Okay. Suppose recursively that we have defined n times m for some natural number n, then we define the successor of n cross m to be this n cross n plus n. Okay, so so then by the principle of recursive definitions, we know that n cross m has been defined for all natural numbers n, and since m is any arbitrary natural number, so here m can also vary. Of course, to use the principle of recursive definitions, we will have to fix m, that's what we have done. But since the thing is true for every m, so we have n cross m for all n and m. Right. Now, okay, one more thing that I must mention. We can, if we want, we can write n plus 1. Okay, because by now we already know and we have seen what the successor of n ultimately turns out to be. It turns out to be n plus 1. Because this is a primitive operation, it is up to you to continue using it or discard it. In place of n plus plus, we can just write n plus 1. That's the point. And one more thing that we should mention at this stage is that since we have already seen all the basic laws on addition of natural numbers, so we will continue to use them from now on without mentioning what we are using. For example, we may use the cancellation law that we have already seen. We may use commutativity, associativity of addition. So those things we will now use without mentioning what we are using. That is, we are not going to write using proposition 2 to 12, we are writing something. I mean, it should be understood that we are using some previous results, okay, that were there in the previous section. Okay, now just like the definition of addition that we came across previously, let us see what happens if we take small values of n. Okay, so first of all, for any fixed m or any natural number m, this is by definition 0. This is coming from the definition itself directly. What is 1 cross M? 1 is the successor of 0 cross M. So by the given definition, this is equal to 0 cross M plus M. And what is 0 cross M? 0 cross M is 0. And we have already seen in the previous section that 0 plus M is M. So 1 cross M is M, which matches with what we expect. Right, so far everything will be alright, but we just have to see how is everything alright. 2 cross M likewise is the successor of 1 cross M. So by this definition, this is equal to 1 cross M plus M. So this is equal to M plus M. If we calculate one more, just like this, 3 cross M will be the successor of 2 cross M, which is equal to 2 cross M plus M. This comes from the definition, but we have already calculated 2 cross M. So this is equal to M plus M plus M. Note that this sum is unambiguous. We don't need to put brackets because of the associative law. So those things we are not going to mention anymore. So this also matches with what we already know. So 3 times M is adding M 3 times, right? So so far things are going the way we want them to go. Now we can just try to look at one more thing that we addressed this question when after we defined addition there in the previous section, that the sum of 2 natural numbers is a natural number. We proved that. Now here also we can prove that the product of 2 natural numbers, the product of 2 natural numbers is a natural number. Remember, since we as yet don't know anything about product other than this definition, this has to be proved. So the proof goes like this. Since this is something that has only been mentioned in the text in the passing, okay, nothing, no explanation has been provided, but nevertheless, for the sake of completeness, we are going to prove it here. So that's why I am not putting any lemma or anything like that. It's just taken as the result. So, and the proof also will be sketchy, just showing the steps. So what I am trying to prove is this: n cross m, right? N and m are natural numbers. I need to prove that this is a natural number. To prove this, I apply induction on n. Induction on n, keeping m fixed. That's how I will start the proof. So when I have n equal to 0, the basis, in that case I have 0 cross m. n cross m is 0 cross m, which by definition is 0. And this is a natural number. Okay. So the base case, in the base case it's okay. We have the basis for our induction. Now next, induction hypothesis. Hypothesis is n cross m is a natural number. I am writing in short like this, okay, is a natural number for some natural number n. This is my induction hypothesis. Then for induction step, I have to show that n plus plus cross m is a natural number. Now what the definition says is this: n plus plus cross m is n cross m plus m. Now this is a natural number that comes from the induction hypothesis, and m is already a natural number, and previously we have proved that the sum of two natural numbers is natural. So that's why this entire thing is a natural number, and here the induction ends, and this gives me the proof of the fact that the product of two natural numbers is a natural number without any doubt. Now I have this. We will now move on to the usual properties that we saw in case of addition. Exact properties are also there for multiplication, as you already know. So the first one is the course commutativity. So it appears as lemma. I should be careful about the numberings of this lemma. Lemma 232. Multiplication is commutative. And this actually has been I should state the lemma at least. Let, although we already know what it means, but still we need to state it properly. Let n and m be natural numbers. Then n cross m equals m cross n. That's what commutativity means. By now we know. And this appears as the first exercise of this section. Exercise 231. So the proof that we will provide here will be a solution to this exercise. And the proof goes the same way we have proved the things so far about multiplication. So let us first, but in case of multiplication, in case of addition, I said multiplication, no, addition. In case of addition, before proving commutativity for addition, we had two initial lemmas. If you recall, if you are able to recall, and one of them, the first one says this: n plus 0 is equal to n, and the second one says n plus m plus plus is equal to n plus m, successor of n plus m. So in this case we have to go through similar things in this proof itself if we have to follow the exact same path that we followed there, and that's the only path and easy path that we know of. So let us first prove m cross 0 is equal to 0 for all because m and it doesn't matter because these are variables. So I can use this m here for all natural numbers. I was thinking of naming it something else, say k or something, but that is not necessary. For all natural numbers, m. Now for this we will use induction. We use induction. And it's clear on what we will use induction, because there is only one variable m, so on that we will use induction. By definition, if we have 0 in place of m, then 0 cross 0 is 0. This comes from the definition itself. Assume m cross 0 is equal to 0 for some natural number m. For some natural number n, then m plus plus cross 0. By definition, this is equal to m cross 0 plus m. We are using the definition of multiplication. And m cross 0 by our induction hypothesis is 0. So 0 plus m. Wait, have I missed something? M cross 0 is 0 for some natural number m, right? So m plus plus cross 0 No, sorry, I made a mistake here. This is not m, this is 0. Why? Because n plus plus cross m is n cross m plus m. So I mistook that m for, I mixed up that m with this m. This will be 0. So this is equal to 0, and this ends our induction. This ends the induction and proves our claim. Right. Now, next what we do, next we prove a similar one. Next, we prove that, let me write it here, n cross m plus plus is equal to n cross m plus n. This we want to prove. For this, we apply induction on m, I think, because m is changing here. Let me just, yes, it's m. Induction on m, keeping n fixed. Okay, so this is another such result. So these correspond to, the first one corresponds to the one for addition, which was, I think, lemma 2 2 2, and this one corresponds to the similar one for addition, which was lemma 2 2 3. Okay, so lemma 2 2 2 for addition we had this n plus 0 is equal to 0. Here we have m times 0 is equal to 0 because this is for multiplication. And for addition, this lemma told us n plus n plus plus is equal to the successor of n plus n. Similarly, here we have n times m plus plus. The expression is different. So these two things, first we prove them. First one we have already proved, the second one we are going to prove them. Okay, so we want to apply induction on m. So note that, so first we will put m equal to 0. So n cross 0 plus plus. Okay, let us just see what it gives us. This is equal to n cross 1. Okay, so we get n cross 1. Note that we cannot write n cross 1 equal to n. We don't know that. All we know is this, 1 cross n is equal to n. This is what we know, and this follows directly from the definition. So we let it sit like this, and then we work with this side. Also, n cross 0 plus n. But we do need this, right? I mean, this will give me n cross 1. Okay, let us see what we get. Now, n cross 0 is 0. Why? Because by this, we have already proved this. In place of m, if we have n, then n cross 0 gives me 0. So 0 plus n. So this is equal to n. Okay, but I don't have n cross 1 equal to n yet. So how do I proceed with this? Let me think. N cross 1, right? What I need is n cross 1 is equal to n. So do I have to prove that also by induction? That will be a pain. It can be proven by induction, but that's not how it goes. N cross m plus n, or have I messed up something here? Not likely. We are using induction. Okay, instead of using induction on n, if I do the opposite thing, if I apply induction on n, keeping m fixed, what do I get then? If I do that, then I will have this instead. Then I am applying induction on n. Okay, so when n is 0, then I have 0 cross m plus plus is equal to 0 by definition of multiplication. and that is equal to, yes, I think this is how I have to prove this. And 0 can be written as 0 plus 0. This 0 in turn can be written as 0 cross m plus 0. So we see that we have this formula when we have 0 in place of n. So this gives me a basis for my induction, current induction. Okay, I think now I am on track. Now I assume the induction hypothesis. Assume n cross successor of m is equal to n cross n plus n for some natural numbers, for some natural number n. Then now I need to calculate n plus plus cross m plus plus. Okay, let me first calculate this. This is equal to, okay, by definition of multiplication, this equals, am I getting it right? Yes, n cross m plus 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 n plus plus. This comes from the definition of multiplication. Or again I have made a mistake, no? Yes, this will be m. Okay, so this comes from multiplication. Now from induction hypothesis, this quantity is equal to this expression is equal to n cross m plus n plus, we already know that m plus plus is m plus 1, right? So we let it sit like this, and now we work with the right hand side. What the right hand side should be when we have n plus plus in place of n. Okay, and I'm continuing from here, and so what the right hand side should be, the right hand side, okay, we can read that out from here. So in place of n, if I have n plus plus, then I have n plus plus cross m plus n plus plus. Now again, by definition of multiplication, if I apply that here, this will be n cross m plus m, and n plus plus, just like m plus plus is n plus 1, n plus plus is n plus 1. Now you see that using the facts that addition is commutative and associative, I can write this expression like this, plus n plus m plus 1, and they are the same. Hence n plus plus cross m plus plus is equal to this. So this completes our current induction, the second induction, and proves the second claim. This completes the current induction and proves the second claim. Now we can prove what we are supposed to prove here, commutative law. Okay, so so here again we will apply induction, of course, keeping one of them fixed. We decide to apply induction on M. Now we prove N cross M equal to M cross N by induction on N, keeping M fixed. Okay, so we straight away move to the induction. We have, so the first case is M equal to 0. 0 cross M equal to 0. This is by definition of multiplication. And M cross 0 is equal to also 0. Now this comes from the thing we have proved in the beginning itself, that I am not mentioning from where it is coming. We have already proved this. That is 0 cross M is equal to M cross 0. So we have this result when N is 0. So this is the basis for our third induction or actual proof. Now we make the assumption. Assume, or we take the induction hypothesis. This is equal to this for some natural number N. Then we look at the case when N is replaced by its successor, N plus plus cross M. This is equal to, if I apply definition of multiplication, this gives me N cross M plus M. Yes. By my induction hypothesis, I get M cross N plus M. Okay. So this is one thing. And at the same time, if I work with the right hand side, to be able to write anything in its place, I need the second result that I have proved, and that gives me this equal to M cross N plus M, and they are the same. So we can just simply, by this observation, we can just simply write this expression here. And this comes from the from what we have already proved before this paragraph, this induction. So this completes the last induction and proves the result. So now we have commutativity of multiplication. Okay, we made some mistakes on the way, but it's natural. Making mistakes is it's not a big problem, but being able to rectify those mistakes is something that we need. Next, okay, next one is important in its own right because of a particular reason. We will see what it means. Lemma 2, 3, 3. the title is something important. Natural numbers have no zero divisors. Let me first state it and then I will try to say what zero divisor is. Let n and m be natural numbers. Then n cross m is equal to 0 if and only if at least one of n or m is 0.